Okay, so pre-calculus 20, McGraw-Hill Ryerson pre-calculus 11 textbook we're in here. 1.3 on page, what page is this here? 32, looks like. So page 32, if you want to follow along in your textbook, you may. So we've talked about arithmetic sequences. We've talked about arithmetic series. And now we're talking about geometric sequences. So we're still talking about a list of numbers, but instead of the numbers being separated by a common difference, this is a little bit different. Okay, we are not actually adding the same thing to each term to get the next. So let's take a look. This is a spider web over here. So you've all seen a spider's web before. It's pretty amazing actually how they make this. It's quite incredible. But if you take a look at the length of the cobwebs kind of within one of these sections, you would notice that there's something interesting. The numbers do not grow by a constant difference. Okay? You're not adding the same thing. Let's say this is an example of a cobweb structure here. So 8 to 12 is 4 units. Now 12 to 18 is actually 6 units. 18 to 27 is 9 units. So it's changing. So is there a pattern that we can recognize here? And that's going to be the key to the geometric sequence. So a geometric sequence, it's explained over here. It's a sequence in which the ratio of consecutive terms is constant. Now I'll talk about this ratio in a second. Okay? The ratio of consecutive terms is constant. Okay, so the ratio between consecutive numbers is constant, and that common ratio is, instead of subtracting one term minus the term before it, geometric means that we're actually multiplying something by one term to get the next. So it's a multiplication thing. And in order to find that common ratio, you take any number in the sequence and you divide the number before it. Okay? So this looks maybe a little bit funny here, but this is the explanation of what a common ratio is right here. You take any term and you divide it by the term just ahead of it. And that's going to be your common ratio. So again, big picture, geometric sequence, it's a list of numbers where you're multiplying the same thing each time to get the next. Multiplying, not adding. Okay? So how does that actually look here? The ratio of consecutive terms in a geometric sequence is constant. So if I had something like this, and here's the example here, I'll use this example. If I had 2, 4, 8, and 16, and so on, if that was my sequence, you can see that I'm multiplying the same thing each time to get the next number, right? And then, of course, the next one would be what? The next one would be 32. Yeah. Okay? So that's what a geometric sequence is. If I didn't know what that common ratio was, you can take any number like 4 and divide it by 2. Or 16 divided by 8. Or 8 divided by 4. Okay? Now, we see a pattern here, and this explanation of the pattern may look a little funny. Okay? You look at this right here in your textbook, and you think, what are all these r's, r squared, cubed? Where is that coming in? Let me show you. So, pen, where are you? Okay. So let's say my geometric sequence starts with a 2, and that's T1, right? T2 is going to be 2 times the common ratio, which is 2. T3 is going to be 2 times 2 times 2. T4 is going to be 2 times 2 times 2 times 2. And so look at what's happening. We have 2 times the common ratio. Then we have 2 times the common ratio squared. Then we have 2 times the common ratio cubed. And so that's where you get this row right here. Okay? So T1 times TR, or T1 times R is the next one. T1 times R squared is the next one, and times R cubed is the third one, and so on. So 2 different ways you can look at it. Take one term, multiply by the common ratio. Then move to that new term, multiply by the common ratio. then move to that new term, multiply by the common ratio. That's one way of looking at it. Or you take the first term and you multiply by r, the ratio, to get the second term. Take the first term, multiply by r squared to get the third term. Take the first term, multiply by r cubed to get the fourth term, and so on. And that's where this pattern comes along. Okay? So the general term sequence here, the general term, for a geometric sequence is this right here. And I'm going to write this a little bit larger over here. T of n, so any term in a geometric sequence is given by starting with t1 and then multiplying by r to the power of n minus 1. Okay. So in our example, if I wanted to find, let's see, I've got 1, 2, 3, 4. If I wanted to find the fifth term here, in this example that we just did, the fifth term, I would take t of 1, which is 2, and I would multiply by 2 to the power of 5 minus 1. Okay, it's a minus there. So t to the fifth, or t of fifth term, would be 2 times 2 to the power of 4. That is 2 times 2 to the power of 4 is 16. So that's 32. And that would give me my next number in this sequence. Okay? So take a moment to digest that. Let me know if you have any questions. All right, example 1 from your textbook says this. In nature, many single-celled organisms, such as bacteria, reproduce by splitting in two so that one cell gives rise to 2, then to 4, then to 8. So we're doubling every time, aren't we? Producing a geometric sequence. Suppose there were 10 bacteria originally present in the bacteria sample. Determine the general term that relates the number of bacteria to the doubling period of the bacteria. Now this sounds a little confusing, but we're just trying to write a formula for this, okay, for what's happening. We're given T1, and we can figure out pretty easily what R is. So that's all we need. And then state the values for T1 and R and the geometric sequence produced. Okay, so we know that T of n formula for a geometric sequence looks like this. It's T of 1 times R to the n minus 1. All right? So determine the general term. So that's the formula for this equation. So we're going to try and fill in T of 1 and R. We need T of 1 and R. So T of 1, n equals, T of 1 here is, suppose there were 10 originally present. That's 10. It doubles every time, so the common ratio would be times what? 2. So R is 2. So I've got 10 times, it's a good idea to use brackets here really, if you can. You don't have to, but it's a good idea. 2 to the n minus 1. Remember, in the nth term formula, you can leave n just as itself. It does not have to be filled in. Okay? Now, what you have to beware here, all right, is you have to beware that you don't do this, okay? Please do not do this. I'll put it in red so you don't do it. This is not the same, okay, as 20 to n minus 1. You cannot combine these numbers first because remember our order of operations? Bed mass, so anything inside the brackets you would evaluate first, then you would evaluate exponents first, next. So that 2 is taken to the power of n minus 1, not the 10. The 10 is not in there. So we can't do this, okay? So your final answer for that would just be this right here, this expression right here. Okay? So that's your answer there for that one. And then we've got T of 1 and R just like it states there. Okay? Questions about example 1? Oh, okay. Hopefully you're getting it. Okay, let's take a look at example 2 then. We've got example 2 ready for us here. Some more work with example 2. So sometimes you use a photocopier to create enlargements or reductions of your original page. Suppose the actual length of the photograph is 25 centimeters. So we've got a photograph and it's 25 centimeters, okay? the smallest size that a copier can make is 67% of the original. Okay? 67%, or 67 out of 100. What's the shortest possible length of the photograph after 5 reductions? So if you envision what's going to happen here, 25 is going to go down by 67%. So it's going to kind of go to this. Then it's going down by 67% again, to maybe this. And then again, and again, and so on. So we're looking for, what is this last little length right here? Okay? And that's a geometric sequence, right? So we're going the original size times 67%, or 67 out of 100. That's going to be our first reduction. Then we're going to go that again times 67 over 100 for our second reduction. And then times that again for our third, and again and again. Okay? So T of 1 is 25 centimeters, or just 25. That's fine. Okay? The R is 67 out of 100, or 0.67. Okay? So 67 out of 100, that's 67%, or 0.67. The T of n formula looks like this, right? T of 1 times r to the n minus 1. And so if I want 5 reductions, like this, I think we should do this. 25 is T1. The r is 0.67. And then we take it to the power of, what's this n minus 1? 4. And so we evaluate that to get us to, 5 reductions, T1. So let me see here. So 1. So after 5 reductions, so that's 1, 2, 3, 4, 5 reductions. Okay. So I think after 5 reductions actually is the 6th term, guys. So I guess we need to go, instead of 5th term, we need to actually go 6th term. Okay. So what's the short length? 5 after 5 reductions. So that is times r, times r, times r, times r, times r. So it's actually the 6th term. My bad. Okay? So that's a good note. We'll have to read that carefully for sure. But so we actually want the 6th term. And then this would be 5. Okay? And so you can calculate that on your calculator, and it should be about 3.375. Okay? That would be rounded. So then your answer would be you can round out to 4 centimeters. That would be your answer. Okay? Questions? Okay. So yeah, just take note on this 5 reductions there. I didn't read it carefully enough myself, but that actually does mean after 5 multiplications of the ratio, right? So we're looking for the 6th term. Okay. So I think this might be the final example I'm going to give you before we just kind of do a little quick summary of the lesson. So let's take a look at example 3 together. Determine T1 and R. So let's say we have to kind of work backwards here, and we have to find out pieces of our formula. How can we do that? Well, the information we're given here is, in a geometric sequence, the 3rd term is 54, and the 6th term is negative 1458. Determine the values of T1 and R, and list the first 3 terms of the sequence. Okay, there's a lot in here. 54 is the 3rd term. So I'm just going to draw this out. I like doing this. Okay. 54 is the 3rd term. And then the 6th term, so 4, 5, the 6th term is negative 1458. Okay, so we have to figure out what R is. Right? 1, 2, 3. So if this is what's going to happen here is 54 is going to be multiplied by r 3 times. So r to the power of 3. And that has to equal negative 1458. Okay, so I'll just say that again. 54 must be multiplied by the common ratio 3 times. So 54 times r times r times r. That's r cubed. Equals this. So we're going to solve for r here. And let's just get the calculator out so we can all see this together. So let's clear that up. So what I need to do is I need to do this. I need to divide by 54 first of all. I'm going to have r cubed equals. So negative 1458 8 divided by 54 is negative 27. Okay? Now how do I get r all by itself here? R cubed. What do I have to do to get r all by itself? Yeah, I have to take the opposite of cubing, and that is taking the cubed root. All right, so a negative value for an odd number in the root sign is not a bad thing. You can take the cube root of a negative number. You can't take the square root of a negative number, right? That's a different side of math that you guys don't know about yet. Imaginary math is what that is. So anyway, so r here, r is going to be negative what? Negative 3? Okay. R is negative 3. Okay. So again, we don't need to know what these terms are. It doesn't matter. Doesn't matter. Don't need to know. What we do need to know though is T1. So, let's work backwards. So 54 equals what? T1, that would be this one that we don't know, times R what? 1, 2. R squared. So let me say that again. I found R here. If we look at this, and that's why I like drawing this out a little bit, because you can actually see, okay, here's T1, and I need to multiply by R times R to get 54. So that's T1 times R squared should equal 54. Set up an equation with one unknown, and you can always solve for it. So T1 is unknown. R is negative 3 squared. Okay. So what is negative 3 squared? That's positive 9. So T1 is 54 divided by 9, which is going to be 6. So R is negative 3, and the first term is 6. Now I think we should check that real quick. We should probably check that. So let's say we have 6 there. What's 6 times negative 3? Don't use your calculator for that one. That is negative 18. What is negative 18 times negative 3? You can use your calculator for that one if you want. But it actually is positive 54, so this is working out marvelously. Okay? Okay, any questions on that? Okay, you might have questions when you get going on the assignment, but let's just take a look at the key ideas first in the textbook here. And again, I'll go through these real quick. If there's anything on here that you do not understand or you think that I didn't cover, please ask before we get going on the assignment. A geometric sequence is a sequence in which each term after the first term is found by multiplying the previous term by a non-zero constant r, called the common ratio. The common ratio of successive terms of a geometric sequence can be found by dividing any two consecutive terms. So take a term, divide it by the one that comes just before it, and that equals r. The general term formula, as we've just been discussing, is T of n equals the first term times r to the power of whatever the 1 less than n is. And that will give you the value of the nth term. Okay, so there's the key ideas, and there is your assignment. Here's your assignment for 1.3. That's 1AC, 2AC, 3AC, 4, 5AC, 9, and 12. So you have about 25 minutes of class time to work on that. If you use that wisely, you might get most of that done in class here. Okay, so here's what those questions look like in your text. In a second, I will. I will in a second. Show in the textbook first. Quickly. Good.
about that.